Thanks for joining us today for our sixth installment of the Sierra Fund's Lunch and Learn series. My name is Nick Graham, and I'm the environmental scientist for the Sierra Fund, and I'm excited to be here today to tell you about the Lake Combie Reservoir Sediment and Mercury Removal Project. To begin, I want to start with a little bit of background. The Bear River watershed is one of Sierra Nevada's most severely impacted by hydraulic mining and mercury contamination. The mercury that was used at these hydraulic mine sites was used to increase the gold extraction process, and many of these hydraulic mine sites remain as sources of mercury contamination to downstream environments today. These mercury-contaminated sediments that travel off of these mine sites can propagate downstream and accumulate behind reservoirs, taking up valuable water storage space. Rawlins, Combie, and Campfire Rest reservoirs that all lie within the Bear River watershed are listed as 303D as impaired for mercury, as well as site-specific fish consumption advisories for mercury from OWIHA, as well as the Bear River as a whole has a fish consumption advisory as well. Lake Combie Reservoir, which is owned and operated by the Nevada Irrigation District, is located in the Sierra Nevada approximately 60 miles northeast of Sacramento and lies within the Bear River watershed between Rawlins and Campfire reservoirs. Upon its creation, Lake Combie Reservoir held 5,555 acre-feet of water storage. NID hired contractors to remove accumulated sediments from behind the reservoir. However, in 2003, this was halted because the dredging of these accumulated sediments was stirring up mercury and violating Clean Water Act standards. Here we have a bit of a project overview. You can see the sediment accumulation within the Combie Reservoir outlined in that black polygon, and this was the material that needed to be removed. However, it needed to be removed in a way that did not cause or worsen mercury contamination in the water body. This led NID to develop an innovative process of sediment removal and treatment, where a floating electric dredge would remove this material and send it through a slurry line to an offshore treatment plant. Surprisingly enough, over a decade ago, the Combie Reservoir Sediment and Mercury Removal Project began with the closed system replicate equipment efficiency tests. These closed system tests, which did not release to the environment, were conducted at Lake Combie Reservoir by NID. These tests indicated that the treatment process removed an average of 93% of the total mercury in the free elemental form within the grain size larger than the 0.63 millimeter. However, the mercury and metals associated with the fine grain materials that were less than 0.63 millimeters were left in the slurry and created by the process. The sediments were treated through the use of a modified centrifuge or a Knelson Concentrator, as you can see pictured on the right in the green equipment. Some next steps were identified, which were to design and test an additional flocculant treatment to remove the contaminated fines from the effluent slurry. Next in the evolution of the Combie Reservoir project was the 2014 and 2015 pilot studies. These studies were constructed as a midpoint between the closed system tests conducted in 2009 and the full-scale implementation at Combie Reservoir to work out any operational unknowns. Pilot studies tested 3 sources of feed material from Combie Pond, the Combie Lake itself, and Greenhorn Creek sediments, which is a similarly impacted region of Rawlins Reservoir within the Bear River watershed. These pilot tests evaluated the coagulant and flocculant types and dosages, refined engineering process set up with the use of settling basins or this blue rain-for-rent tanks, as well as water samples were collected throughout the treatment process to evaluate the system's ability to reduce sediment and mercury concentrations. Following completion of the pilot tests, coagulant and flocculant types and dosages were chosen and calculated. Settling tanks in the basins were evaluated as necessary. Some operational efficiencies were identified, such as screening the largest grain material first and the feed rate into the system, as well as the need for real-time monitoring became apparent. Before we get into the full-scale implementation, I want to go over a few project purposes and objectives. First was to remove these accumulated sediments and mercury from Combie Reservoir and restore the reservoir capacity for ag, domestic hydroelectric power generation, and recreational use. Next was to measure and analyze ecological effects of methylmercury concentrations in Combie prior and post-removal activities. Next was to develop an efficient, compliant, and sustainable combination of processes for sediment removal at other similarly mercury-impacted reservoirs within the state. Next was compliance monitoring to evaluate and document compliance with permits and regulations, performance monitoring to evaluate the effectiveness and the cost per unit of sediment and mercury removed, conduct environmental monitoring, which was well beyond the compliance level, but we wanted to evaluate changes in mercury concentrations in biota and environmental media at locations both above and below the process site, as well as before and after the sediment removal. So we can begin in 2008 with the dry excavation. Combie Reservoir presents a unique opportunity that following Labor Day, the reservoir lake level is dropped, exposing these accumulated sediments above the water surface at the upper reaches of the reservoir. This opportunity presented an ability to remove these accumulated sediments in the dry, which is significantly operationally cheaper and allowed NID and Great Lakes Environmental and Infrastructure to essentially drive out onto these deposits and remove sediments by excavation rather than dredging. If you look at this picture, you can see the road, which is made of essentially large railroad ties or mats that allowed the excavators out onto the deposits to remove the accumulated sediments. Silt fencing or curtains were also constructed around the deposit, which you can see kind of in a black outline around that peninsula. And these were placed around the entire deposit to limit any calving effects that might affect downstream water quality during the excavation. Environmental consulting firm NV5 also conducted an extensive soil testing of the deposit prior to excavation, which oriented the excavation process to prioritize areas of the deposit that were found to have a higher probability of mercury concentrations. Now, if you look at this picture, we're facing 180 degrees in the opposite direction from the previous photo and facing downstream. Here you can see where the excavation essentially skimmed the deposit and removed approximately 38,000 cubic yards of sediment. 6,000 of these cubic yards were actually separated for processing the following spring once the processing plant was set up. These 6,000 cubic yards that were separated were identified through NV5 soil testing as having a higher probability of containing the greatest mercury concentration. So, in the spring and summer of 2019, the removal process pivoted from a dry removal approach to a wet or dredging of accumulated sediments. Although the removal in the dry was more economical, the process served largely as a proof of concept to develop best management practices for similarly sediment-impacted reservoirs in the state. The suction cutter head drudge would essentially sweep back and forth from the barge seen above, making approximate 5-foot cuts into the sediment each time. From there, the slurry was pumped through the floating pipes, as you can see with those orange buoys in the photo on the right, approximately 1 mile upstream to the processing plant for sediment and mercury removal. What you see within the yellow silk curtain is the resuspension material caused by the activity of the cutter head. Here we are looking at a bathymetric survey of the area of which was dredged from the barge. You can essentially see those sweep marks where those cuts were made from the removal of the sediment. An estimated 10,000 cubic yards of sediment were dredged during the wet dredging process for a total of 48,000 when you combine the wet and dry periods. Pictured above is a photo of the processing plant. This processing plant was essentially split up into 3 parts. Mechanical separation or sieving of the larger grain materials as the first order of operation through a 10 mesh screen size. The second was pumping of the remaining slurry through a large centrifuge or the Knelson Concentrator that would remove the liquid elemental mercury. And the third part was a water treatment process to remove the remaining sediment from the effluent before released to the reservoir. The use on this innovative design was a modified Knelson Concentrator. The Knelson Concentrator is used in gold mining operations as a technique to recover fine-grained gold. The Knelson Concentrator received a slurry of about 10 to 15% solids, or at around 480 to 600 gallons per minute. The Knelson would then rotate at high velocities, creating around 60 Gs, and the gold and mercury with a specific gravity of 4 or greater would be separated. The high-density free liquid mercury was spun out of this solution, and the remaining sediment would go on to the next treatment step, as you can see denoted in those yellow arrows. The effluent from the Knelson concentrator would then be treated with a flocculant and sent through a series of settling basins. The water would essentially flow from the bottom right of the picture to the top left of the picture, and each step gaining more and more clarity. Next, I want to take a step back and explain what the coagulation and flocculation process looks like. This is a simple explanation on the effect of coagulant and flocculants have on suspended sediments in the water. First, a coagulant is added that strips the repulsive charges from the individual particles or colloids and begins the coagulation effect and creates a larger particle size. Then a flocculant is added that essentially sweeps these newly formed coagulated particles into an even larger, heavier form where gravity takes over and they begin to settle out of solution at a greater rate than untreated. Many times, a coagulant and flocculant are combined for a single dosing agent, such as in the case for Combie Reservoir Sediment and Mercury Removal Project, where a flocculant called chitosan was used. And chitosan is in fact an organic biodegradable compound made from shellfish. In the photos above, you can see the progression of flocculant treatment and its effect. On the left photo, you can see the black pipe, which is where water being pumped from the Knelson Concentrator's tailing ponds, being treated in line by the coagulant, and then dumped into the second detention pond or settling basin. Once that pond was full, which took approximately 1 day, the pond was left to settle overnight, and the resulting water is what you see on the photo on the right. I'm sorry for the glare in the photo, but if you look closely, you can see clear to the bottom of the pond. From this point, the water would be ready for release back into the Bear River or Combie Reservoir. However, the infiltrates of these settling basins were greater than the process was able to produce, thus resulting in the process not releasing any effluent back into the environment, which was an unexpected benefit. In the event that water would have been released to the Bear River, there was a real-time monitoring data collection platform, or DCP, in place that could confirm the water quality would meet regulatory standards and provide real-time information to the plant operator, allowing for adaptive management. The real-time monitoring component of the Combie Reservoir Sediment and Mercury process happens to be my favorite piece of the project, but I might be a little biased. There were 2 data collection platforms that were outfitted with multi-parameter water quality sensors, ruggedized data loggers, and wireless modems. Data collected could then be relayed in real time to a project manager and operator. DCP stations were located at the upstream end of the project, known as LC1, and that represented the background water quality, and also at the most downstream end of the process following treatment, but prior to release, denoted as LC2. If the process effluent was to be released back to the reservoir, LC2 data would be compared to background data collected at the LC1 station. The most exciting piece of the use of these monitoring stations was the development of a predictive mercury concentration model. Pairing the data collection of the multi-parameter sensors with grab samples for mercury and dissolved organic carbon provided us with the data set necessary to build a model. Once the model was calculated, the model could be programmed into the data collection platform to predict real-time mercury concentrations in addition to standard water quality parameters that project managers could have access to from any remote device. Having the ability to calculate statistically significant mercury concentrations instantaneously is revolutionary in the realm of trace metal sampling. For Lake Combie and other similarly situated reservoirs within the Sierra Nevada, this framework of data collection will facilitate the growth and scale of addressing mercury contaminant sediments within the reservoirs. On this slide picture on the left, you can see a time series of filtered and particulate mercury concentrations throughout the process. The middle picture, you can see something is what I call a daily report, which is something that data collection platforms can produce and send out to project managers and operators on a daily or weekly format. And then picture on the right is the water quality sensor on one of our monthly maintenance visits. In addition to real-time monitoring, there was extensive environmental modeling being conducted and carried out by the United States Geological Survey. And the results of these sampling events will be presented at our Headwater Mercury Source Reduction Workshop this fall, so please stay tuned and join us. The monitoring efforts that have been taking place are fish tissue, water sampling, zooplankton, sediment, and pore water sampling, all for total methyl reactive mercury concentrations, as well as additional parameters such as dissolved organic carbon and a suite of nutrients. So what did we learn? We learned that removal in the dry should be pursued whenever possible. We learned that dredging with this suction cutter head dredge, a turbidity curtain, and the monitoring can safely remove mercury-contaminated sediments without degradation of downstream environments. We learned that the real-time mercury monitoring can facilitate projects in mercury-contaminated deposits, from reservoir maintenance to floodplain restoration. And finally, I want to end with a big thank you. The interdisciplinary working group of experts on this project led to an innovative, reproducible approach to addressing reservoir sedimentation, utilizing techniques from the mining, water treatment, dredging, and engineering industry. The completion of the Combie Reservoir Sediment and Mercury Removal Project proved that sediment removal activities can be done in an environmentally protective manner and be replicated at other similarly impacted water bodies in the state. The Sierra Fund is proud to have been a part of this project, and we all learn from each other. I want to thank everyone involved for their willingness to share information, offer meaningful contributions, and their willingness to try new things and be inclusive. So thank you. And finally, I want to thank all of our project partners and funders at NID, Great Lakes, NV5, USGS, permitting agencies at CDFW, Department of Water Resources, and the U.S. Army Corps of Engineers, as well as the primary project funding from DWR. If you have any other additional questions, please feel free to reach out and email either myself or Dr. Carrie Monahan. And thank you for listening.